Alright guys, we made it to our last set of notes for Unit 1, Notes D. Today we're going to talk about phases of matter. Before we can talk about how different phases change into each other, we have to talk about the theory behind it. Kinetic molecular theory is one of the most important theories that we're going to talk about in this class, and it's one that comes up all the time. Kinetic molecular theory, or KMT, talks about the motion, remember kinetic means movement, of molecules. Now think back to laws versus theory. What do theories do? Theories explain, so the kinetic molecular theory would explain molecular motion. So there are three postulates under KMT. The first says that all atoms are made of tiny particles. Particle motion is actually an important thing as opposed to wave motion. It makes the math much simpler. So yay, particle motion. The second postulate says that as particles are in motion, if they have a higher temperature, they would move faster. So to sum that up, increased temperature equals increased kinetic energy. They move faster. The third postulate says that assuming the temperature is the same, if you look at mass, the heavier particles will move slower. So if I increase the mass, then the particles are slower. So we want to keep in mind for phase changes, mostly the second postulate, although the third postulate will come up again. Let's start with some basics on the three main phases. So solids have a definite shape and a definite volume. Those molecules are tightly packed, but what you might not think about is that there is some motion. There's only one temperature that we know of that particles completely stop motion, and that's called absolute zero, and that would be 0 on the Kelvin scale. Since it's not absolute zero in most of the real world, we have vibrating particles. You might look at your desk right now and it does not seem like it is vibrating, but if you zoomed into a particle level, those particles would be vibrating. Liquids do not have a definite shape, but they do have a definite volume. Their shape can change as they flow and they pour. They can get poured into a different container, take a different shape. The resistance to that flow is something called viscosity. So that's a vocabulary word there. Viscosity is the resistance to flow. So something like honey would have a high viscosity, whereas water, rubbing alcohol would just kind of flow, would have a lower viscosity. And then we have gases, which do not have a definite shape or a definite volume. You can cause gas particles to get closer together if you compress them, and you can also expand the walls of the container, and they would expand to fill it. This is a very unique property that we're going to talk about a lot in several different units in this class. We call it compressibility. It's about how the particles can spread very far apart or could be compressed together. It is the only one of the three phases that has this unique property where it will expand to fill the container or be compressed into a smaller container. And that's because gases are the only thing that do not have a definite volume. We need to know what the phase changes are called as well before we get into what's happening at each one. Let's start with solid to liquid, some phase changes that you're probably familiar with. If you go from the solid to the liquid, like ice to water, we call that melting, and liquid back to solid is freezing. If you're going from gas to liquid, we would call that condensation, whereas if you're going from liquid to gas, I would call that vaporization, to be very general and talk about the just phase change as a whole. We also have heard that called evaporation when you're just talking about like water out in the world, but there's also something called boiling. So I'm going to go with vaporization to talk about it just generally speaking. And then something that's less common, the solid straight to the gas, we call that sublimation, like with dry ice. And then there's something else where the gas turns back into a solid, we call that deposition. Think about how the gas would be depositing. Seemingly out of thin air, you're getting solid particles. So it looks like deposits, deposition. What kind of change was a phase change again? That's right, all phase changes, regardless of which one of the sets we're talking about, all of them are considered physical changes. So remember that. The main thing that we want to focus on when we look at these phase changes one by one is the energy transfer. So energy is defined as the ability to change or move matter. So the most common form of energy, or the one we'll talk about in chemistry, I should say, most often, is heat energy. So energy is either going to be released, heat would be released, or it would be absorbed. So we have two key terms for that. And these are super important vocabulary words too. An endothermic process would absorb heat, and an exothermic process would release heat. Just a little trick, you can think the EN for enter and EX for exit, showing that the heat is exiting or being released, or the heat is entering in endothermic or being absorbed. So let's start by looking at melting and freezing a little more closely, focusing on the energy. We know that the solid particles are very close together, whereas the liquid particles are far enough apart to be able to slide over each other. So which do you think has more energy, solid particles or liquid particles? The liquid particles would have more energy. The solid particles, having less energy, would be moving less, so they would be closer together. What law or theory says that as particles increase in temperature, they increase in movement? How did you know that the liquid particles would have more energy? Yep, that would go back to our very first slide, kinetic molecular theory. That is the theory behind all of these phase changes and how the energy affects them. Now let's talk about the actual energy transfer. In order for the solid to turn into a liquid, it has to go from less energy to more energy. So it has to gain energy. A gain in energy would be an endothermic process where the energy is absorbed. In order for the liquid to go back to a solid, we have to go from more energy to less energy, meaning we have to lose energy, which is an exothermic process where energy is released. Usually there's only one temperature where this transition occurs. So both melting and freezing would occur at the melting point. There's no need to call it also the freezing point. It should be understood that both of those things would occur at the same temperature, and so we just name it once and we call it the melting point. Now let's look at the transition between liquid and gas. Which would have more energy? The liquid particles, which are close enough together to move around each other, or the gas particles, which are spread apart as far as possible? The gas particles, in order to be spread out that far, would have to be moving the fastest, so they would have the most energy, where the liquid would then have less energy compared to the gas. So if we're looking at the liquid turning into the gas, would it need to gain or lose energy? Going from less energy to more energy, it would need to gain energy. So that would be an endothermic process where the energy is absorbed. In order for the gas to turn back into the liquid, it would need to lose energy to go from the most energy down to less energy. And that's exothermic, where the energy is released. Both of those transitions happen at the boiling point. And here you see we can call it condensation, or they have the two different forms of vaporization, evaporation and boiling. Any transition between the gas phase and the liquid phase would happen at the boiling point. This diagram combines all of that information. Here we have the solid at the bottom with the least amount of energy, then the liquid in the middle, and the gas with the most amount of energy. As I move up from solid to liquid, I gain energy, and as I move up from liquid to gas, I gain energy. These are both endothermic processes where the energy is absorbed. As I move down from gas to liquid, or move from liquid down to solid, I'm releasing energy, losing energy in an exothermic process as the energy is released. Now I want to expand our thinking just a little bit. Everything that we just talked about is what the particle needs. If a particle of solid wants to turn into a liquid, it needs to absorb energy. But if that particle of liquid wants to turn back into a solid, it needs to release energy. What we haven't talked about yet is that does not occur in an isolated system. that energy cannot just magically appear or magically disappear. By the way, how do we know that? What law or theory states that matter, or energy, I should say energy, cannot be created or destroyed? That's right, the law of conservation of energy. So in order to follow that, if the energy is absorbed, there has to be something that would then release energy. So that has to come from somewhere, like the surroundings. So on the right side of this diagram, where the energy is being absorbed by the particle, the surroundings around the particle would then have to release energy. And on the flip side, whenever the particle is releasing energy, the surroundings around it would then get warmer, having to absorb that energy. So it's always kind of a complementary system. If the energy is being absorbed by the particle, it's released by the surroundings, and vice versa. Now let's look at the difference between evaporation and boiling. So both of these are where the liquid is turning into a gas, but evaporation is kind of automatic. It's just this random motion where the particles are escaping from the liquid surface. The energy is going to then be absorbed by the substance because the energy is being released from the liquid surroundings. Let's look at an example in order to get a better understanding of what part of this is the particle and what part of this is really the surroundings. So picture a puddle getting shined on a nice bright sunny day, and I have this little particle at the top of the puddle that wants to evaporate. That particle is currently a liquid and it wants to become a gas. So would it need to gain or lose energy? Well, the particle itself would need to gain energy. The energy is absorbed by the substance. Then the energy has to come from somewhere. So not only is the bright, shiny sun an obvious source of energy, but it's going to take it from all sides. It's also going to pull energy from the liquid around it. So the liquid surroundings actually lose energy as well. So that's going to cause the liquid body to cool off. Have you ever jumped in a pool in a hot summer day? And if you jump in the deep end and go too deep, it is really cold down there. The water is not only just too far from the sun, it is losing energy to the particles on top of the pool that are evaporating. Evaporation occurs only at the surface. Let's see if you're getting the hang of this. Consider both the particle and the surroundings. True or false? Evaporation is a cooling process for the human body. That is true. The particle itself needs to leave, so think of the sweat, needs to leave the human body. So that sweat particle is liquid, it wants to turn into a gas, just like the particle we talked about in the evaporation example. So it's going to absorb heat from all sides, including the human body. The human body in this case would be the surroundings, and it would be losing energy to the sweat particle. Now let's talk about boiling. It's very similar to evaporation in that it's also when the liquid turns into a gas and you're going to have very similar energy things going on. But it is different in the sense of where the boiling actually occurs and where the heat is applied. So when you boil a substance, typically the heat source is at the bottom. Think of boiling a pot of water. And so that boiling needs to actually occur throughout the liquid. Say we have a pot of water and we're trying to boil it. We have one little particle here that wants to become a gas. So it, just like the other particle, needs to gain energy. That energy comes from the surroundings, kind of like the sun. The hot stove could provide some energy for the particle. But as the particle goes up to escape, it's going to be losing energy because the particles next to it would be cooler, and heat always flows from hot to cold. So until all the particles are the same temperature, that little particle is not going to be able to escape. Speaking of being able to escape, it also has to worry about the pressure from the air pushing back down on it too. which is not something that we're worried about in evaporation. Boiling actually does depend on pressure. This picture might help you see the difference a little bit better. The evaporation occurring only on the surface, the particles beneath do not need to be heated, whereas the boiling has to occur throughout the substance in order for the particles to be able to escape. Next, I want to talk a little bit about how boiling depends on pressure, but before we can get there, I need to define something called vapor pressure. So this is an important definition. I have a little diagram that I draw with this just to kind of help me remember the definition. It's not the perfect actual reality of what's going on with vapor pressure. First, I'm going to start by drawing a square and then picture this as like a 3D fish tank. That's going to represent my closed container. It would be completely sealed on all sides. In this little fish tank, I have some liquid water, and then I also have some gas or vapor. The vapor pressure is the pressure that the gas puts on the liquid. The pressure exerted by the vapor on the liquid, or on the surface. So it does say of the liquid. So what that means, the vapor of the liquid, what that means is these two substances would have to both be the same, so H2O. Equilibrium is something that we'll talk about a lot at one point, but just picture that this is kind of a status quo, like it's not changing much. So whatever that pressure is from the gas pushing on the liquid, not on the walls of the container at all, just gas onto liquid, that's defined as the vapor pressure. And the vapor pressures of substances do depend on temperature, but they can be looked up. There's more of an appendix type of piece of data. So we have standard vapor pressures that we can then compare different boiling points to. Before we move on, just real quick, why does it increase as temperature increases? Well, you would get more and more gas as the temperature increases, because you would be having more and more particles turn into gas. You'd be getting more energy in the system, and so that would create more of a vapor pressure, more of a push down. This is an example of something we call a vapor pressure curve, which shows that the vapor pressure does increase as temperature increases. But I also think looking at this curves helps you understand it's not necessarily a linear progression. It's actually more of an exponential progression. So you're really going to see a great increase in the pressure of the gas as you get more and more energy into the system. Another really cool thing about this graph is that you can actually use it in order to find the boiling point. For example, they have 760 annotated on here. That's actually just normal pressure, like sea level, the equivalent of 1 atmosphere. If we look at that, it goes down to a temperature of 100 degrees. That's why we know water to boil at 100 degrees, because we're normally at a normal sea level. If you go up to a higher elevation, you might be at a lower pressure, and that stuff might boil faster. You could be at a lower temperature. So theoretically, if we dropped the pressure way, way down, we could boil at room temperature. There's actually something called a bell jar that does just that. It sucks the air out and allows the water to boil at room temperature. And then if you touch the water, it's not even hot, but it does boil because we've dropped the pressure. So this vapor pressure curve is one of your 3 important graphs in order to be able to determine the boiling point. So now that you kind of have an idea of what vapor pressure is, keep in mind that that's kind of just how we determine what the vapor pressure is, but that pressure in real life would be the pressure out here in the atmosphere that's pushing down on the liquid that's trying to boil. You can only get boiling if the vapor pressure is at least equal to the atmospheric pressure. So if the gas is strong enough to overcome the pressure coming in from the atmosphere, then we could have boiling. So why doesn't the vapor pressure matter to evaporation? Well, in order to boil, we would need bubbles to form so that the bubbles can rise to the surface and to escape. We don't need bubbles in evaporation. Evaporation happens only in the surface. So the vapor pressure isn't going to bother the gas formation for evaporation, but it will interrupt it for boiling. You may have seen a pressure cooker. You might even own one. How do you think that using a pressure cooker or cooking at a higher pressure would help the food cook faster? What happens is the higher pressure means that the water boils at a higher temperature. So we get a higher temperature in which to cook our food. Hotter water, hotter food would cook faster. There's more energy available for the food that's cooking. The last thing that we're going to do in these notes is look at three very important graphs, the first one being the most important at all. So in this graph, we're going to look at what would happen if we took an amount of water. The example here says to imagine that we have ice that's negative 20 degrees Celsius. So the idea is that you start off lower than 0 degrees Celsius, and then we're going to apply heat and look at what would that graph look like if I recorded temperature over time. It might surprise you, but there would actually be some plateaus. It turns out that as a particle is undergoing a phase change, it does not change temperature. This is actually an effect of the conservation of energy. The energy is going into breaking apart the particles, making them space out further, so there's no energy for a temperature increase. It's one or the other. So the plateaus that you see here would represent your melting points and your boiling points. At those melting and boiling points, you're going to get your standard phase changes. So at your melting point, you get melting and freezing, and at your boiling point, you get the condensation and vaporization. The solid would be below the melting point, whereas gas or steam or water vapor would be above the melting point, and in between, of course, would be your liquid. If this were the phase diagram, or heating curve I should say, for water, then we should also know and label the temperatures that we do know on the y-axis. So what is the melting point of water? Typically 0 degrees Celsius, and the melting point would be 100 degrees Celsius. I'm pointing that out now because it's going to come up when we study heat. The other thing that we need to know about this graph is which parts represent stored potential energy and which parts represent kinetic energy. We're changing the stored energy when we're changing the spacing in the particles. There's actually something called intermolecular forces in there that's actually changing. So we're kind of changing a bond energy in a sense. That's stored energy. So those potential energies are going to be found on your plateaus. P for plateau, P for potential energy, right? The kinetic energy would be when the phases are actually increasing in temperature. By the way, what was that very important definition for temperature? Right, temperature is the average kinetic energy of the particles. So kinetic energy changes when the temperature is changing, literally by definition. The second graph is called the phase diagram. The phase diagram is going to show how the pressure and temperature relate to the phase changes as we go from solid to liquid to gas, or even just between solid to gas. First, let me point out what's going on with the phases themselves. Notice this one's specifically for water, so they call it ice, water, and steam. You could also generically say solid, liquid, gas. So at the lowest temperature, notice temperature is low on the left of the X column. We have the solid, and if you go straight across, we're into the water zone, and then as you increase the temperature to the highest temperature, now we're in the steam zone. So the easiest way to remember the phases is just follow your temperature from low to high. There are two other important points on this graph that you should know. In the center, where all three phases combine, we have something called the triple point, which would be where you would theoretically simultaneously have all three phases present. We also have something up here called the critical point, which would be the maximum temperature and pressure for a stable fluid. Beyond that, we call that thing a supercritical fluid. Not all phase diagrams are created equal. As a matter of fact, water is one of the few known that actually has a Y shape that bends backwards. Notice that CO2 goes not only a little bit forward, but it also starts up much higher. That's going to explain why at 1 atm, which is called normal pressure, the pressure at like normal sea level on Earth, you're going straight in between solid and gas. Whereas if you look at 1 atm for liquid water, you're going from the solid to the liquid first. So you've got two different phase changes happening at the same pressure. It all depends on the phase diagram for the specific substance. Last thing is the lines themselves actually have names too, not just the 2 points and the 3 phases you need to know. You also need to know these 3 lines. So the line between the ice and the water where melting would occur is called the melting curve. The line between where sublimation and deposition would occur is called sublimation curve. And then this might look familiar from earlier, the line between where steam and water, or vapor pressure curve. That's the one that we used that also had temperature and pressure, and we were able to determine the boiling points. So we already talked about the triple point and the critical point. Triple point you see here in the middle where all 3 phases would coexist. That's a good word there. And then the critical point would be the one kind of at the end of the Y in the top right. That point is going to be where you reach something called critical pressure and critical temperature, or earlier we said that's where you find your supercritical fluid. So just to define that a little bit more, critical temperature is the temperature above which the gas cannot be liquefied. Well, if it cannot be liquefied, then that means it has to be a gas, right? Well, critical pressure is the pressure required to liquefy a gas, meaning it isn't going to be a gas, it's supposed to be a liquid. So is it a liquid or is it a gas? It's having an identity crisis. It's gonna blow. So we call those very unstable supercritical fluids. All right, guys, that wraps up the end of our notes for Unit 1. Not only just Notes D, but this is our last section of notes for Unit 1. So make sure that you annotate all of your notes from Unit 1 with questions, come in, and be ready for your test.